of the atomic models. In the previous part, we went over the quantum mechanical model, all right? Going hand in hand in understanding how atoms work is something known as the electronic configuration, right? So, protons and neutrons aren't much of a mystery, they're just there in the central dense nucleus. It's electrons that are very hard to track. But there's a system known as the electronic configuration to try to figure out where electrons are in their energy levels, in their sublevels, and in their orbitals, right? So, electronic configuration, in simple words, is how electrons are arranged in an atom. Now, there is something known as the diagonal rule, okay? It's a very helpful rule to figure out how electrons are arranged in a certain atom, okay? So this is how you do it. At any time, you can write it down yourself. I'll show you the easiest way to do it, okay? Write numbers 1 up till 4 like this. 1, 2, 3, 4, all right? And then write it like this, 2, 3, 3, 4, 4, 4, right? Simple enough. In the first row, write S. Remember, do you recognize S as the sublevels, right? So the first, we know, if you look back at the previous table, I'm just writing it in a new way. We know that each energy level has the sublevel S, all right? We know the second, the third, and the fourth also have the sublevel P, so I'll write that P down here. And we know the third and the fourth also have the sublevel D. We know the fourth additionally has the sublevel F, okay? Now, let's think back to how many electrons each of these sublevels can hold. All the S's can hold 2 electrons, right? All the P, which has 3 orbitals, can each hold 6 electrons. All the D, which has 5 orbitals, can each hold 10 electrons. And all the F's, which have 7 orbitals, can hold a maximum of 14 electrons, okay? So it's much easier. Once you understand what this thing looks like, it's much easier to draw it whenever you need it because it's really helpful in the electronic configuration. Now, let me change my color and explain to you why it's actually called the diagonal rule, okay? The diagonal rule, it's because you draw diagonal lines like this. Boom, and boom, and boom, and boom. Boom, boom, boom. You might think why I just crossed out all of my work. Well, consider the yellow lines how you would read this diagonal rule. Consider what these lines cross out, okay? Let me write it again in the side here. That's what this blue space is here for. Okay, let's look at what each of these diagonal lines cross. We see the first thing that the first diagonal line crosses is 1s2, right? Does it cross anything else? No, it doesn't. So let's go to the next diagonal line. We see the next diagonal line crosses 2s2. Okay, anything else? No. Let's look at the third diagonal line. The third diagonal line first crosses 2p6, right? And then it crosses 3s2, right? Next, let's go to the fourth diagonal line. It first crosses 3p6, and then it crosses 4s2, and it just goes on and on like that. 3d10, I don't have much room, but it goes on and on and on like that, okay? This is what we call the electronic configuration. Now, you might think, where did this order come from? Well, this order comes from a principle known as the Aufbau. It's a German word, I think. The Aufbau principle. This says that electrons must occupy a lower energy level before it occupies a higher energy level, okay? So electrons must fill the 1s orbital before it fills the 2s. And it must fill the 2s before it fills the 2p, and the 2p before it fills the 3s. Now, there's a formula for the Aufbau principle and how to apply it, but this diagonal rule just simplifies the process for you, right? Just draw this 1s2, 2s2 formation, draw diagonal lines, and there you go. That's the order. All right, you don't have to use some philosophy or anything like that. It's right there. That's the order. 1s is less than 2s, 2s less tn 2p, 2p is less than 3s. It might seem random, but the great thing is you use this so often that you'll be able to memorize it without even knowing. Like, I can say it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Anyway, this is the electronic configuration, and it's a beautiful way to figure out where electrons are. Now, a good way to understand how we can actually use this is obviously with an example. Let's use chlorine. Chlorine has an atomic number of 17. Now, remember, atomic number is the number of protons, but it can also be the number of electrons. Let me just tell you that this chlorine is stable, it's neutral, so the atomic number 17 also can be used for the electron number. So we say 17 is the number of electrons, okay? It's also the number of protons, but we don't care about protons right now. We're looking at the electronic configuration. So if you don't remember what the electronic configuration was, draw out the previous diagram. But if you do remember, write out the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. All right, we don't actually have to go this far, but I just want to show you how it would all look like. But we don't have to go on continuously. We just have to reach 17, okay? So let me get rid of all these number of electrons at the top. Let me get rid of these electrons up here, right? So 1s2. We're trying to get up to 17, all right? So we have 2 now. 2s2. 2 plus 2 is 4. We're not at 17 yet. 3p6. 2 plus 2 plus 6 is 10. Not at 17 yet. 3s2. 2 plus 2 plus 6 plus 2 is 12. Still not at 17. 3p6, right? 6 is the maximum. But if we add 6 to this, we're going to be at 18. We only need to be at 17, so we just have to say 3p5. And the other orbitals are empty, so we can just get rid of that, okay? So you can use any method you want in order to get the sum of the top elements, or the sum of these electrons right here. Any method you want to get this sum to be equal to 17, okay? So that's the whole point, or whatever the atomic number of the element may be, right? All right, so what does this mean, okay? We see that we have 1s, we have 2s, we have 3s. So we know we have the 3 energy levels. There's no 4. We have the first, the second, and the third energy levels, okay? This is how you write the electronic configurations when we're talking about the sub-levels. When we're talking about the sub-levels, right? If you want to write it in terms of the energy levels, okay, just look at each principal quantum number. So let's start with 1. How many electrons do we have in 1? Only s2, so only 2 electrons, okay? What about in the second energy level? We have 2s2 and we have 2p6, so we have 6 and 2, we have 8 electrons, okay? Finally, we have the third principal quantum number, we have 3s2 and we also have 3p5. 5 plus 2 is 7, okay? This is how you write the electronic configuration in terms of the energy levels, okay? Each number represents how many electrons there are in each energy level, okay? The first, 1s2, 2s2, 2p6, and all that is how you represent it in terms of the sub-levels, and 2, 8, and 7 represents the energy level. So if you see something like 287 or 2818 or whatever it may be, know that each comma represents the number of electrons in each energy level. So 2 is the number of electrons in the first energy level, 8 is the number of electrons in the second energy level, and 7 is the number of electrons in the third energy level. So that is all for the fourth subunit and final subunit and the total first unit of grade 9 chemistry. This unit is the foundation of all chemical concepts here to come. So I strongly recommend, if you need to, watch the videos again, do sample questions, read your reference textbooks for more information, and stay tuned for the second unit of grade 9 chemistry. Thanks for watching.